So let me just remind everybody of the due dates I have implemented on my math lab now. So today will be the last new material that I go over after this. Wednesday's class session will be the final exam review. And if we should have a little bit of time at the end of class. I can mention some brief stuff on it, but mainly we're going to go over everything on Wednesday. But I'll be covering the last section here, test for population means, and that is due on the 5th, that is Wednesday. There are 6 questions on it, and some of the questions should have a very similar process to 10-2, as we'll see momentarily. And then the corresponding quiz is due Friday. Then as far as that goes, those are the last 2 assignments for this class. It's those 2, and then the final. Those are the only assignments for this class. And after the homework is due on Wednesday, I can go ahead and drop the 2 lowest homework grades. So that is part of this class. I drop the 2 lowest homeworks. And then after you turn in the quiz, I'll drop the 2 lowest quizzes, which that should, I believe I've looked at some of your grades. For some of you, that should be a pretty reasonable boost to your grade by dropping the 2 lowest quizzes. Because there's a lot less quizzes than homeworks. In fact, there's only, looks like 8 quizzes here. So dropping 2 of those, that's very substantial. So aside for that, so there's a homework on Wednesday, quiz on Friday, and then the final is on the next Thursday, on the 13th. Again, I'll send out more information about that as that comes. I believe it's Thursday the 13th at 8 a.m. I believe that's the designated time spot, and we will be taking that test in here. We will take the test in here. It'll be a paper test, of course. Again, I'll mention more details about this on Wednesday, and I'll be sending out an email to make sure everyone remembers. But besides for that, does anyone have any questions for me before we get started? And I did decide that the final is not going to be cumulative. It's only going to be chapters 8, 9, and 10. So I feel like that's plenty of material to go over. So not cumulative. So I figured that's something else you'd all like to know. But besides for that, let's go ahead and move on to the last section of the class. And naturally, as we did in previous chapters, where we went from looking at one parameter to another, we do the same thing here for hypothesis testing. We go from looking at population proportions to population means. And really, the process is very similar. Now, aesthetically, the first thing that you may notice is that the test statistic, so I'm going to compare this a lot to the last section because they're very similar. They're really similar because for this p-value approach, that we're doing, where we get a p-value, we did this in the last section. The reason why this is so symmetric to the previous section is because we're throwing a bunch of this into the calculator. So it's kind of difficult to go wrong in the midst of the process. The primary concern is, can you set it up correctly? You can set it up correctly. There's not really too much room to go wrong unless you type it into the calculator wrong. Now, you might remember from the previous section, the test statistic that we used they used the variable z instead of a t, which doesn't really change anything. It's an aesthetic choice. It's a different formula. It is a different formula. But again, if we're throwing this into the calculator, who cares if it's a different formula? It's going to take care of everything off to the side. The only way that translates to us is that we're going to use a different calculator command. And that's going to be your goal ultimately for the final, to realize which calculator command do you use. And the t, this t with a little 0 next to it, t naught, as it's called, this indicates, well, the t indicates that we're using a student's t distribution, which we talked about in section 10.1. So it's not a normal distribution, it's a student's t distribution. We talked about some aspects of that in section 10.1. But furthermore, what this practically indicates for us, what we care about, is that we use the t-test in the calculator. And if you scroll down, if you have the notes printed out, you'll see the t-test stuff on page 96 of the notes. So again, it's a very simple process. We follow it almost symmetrically to before. Instead of the one proportion z-test that we did in the last section, we just use a t-test. And so that means because of the calculator, we can ignore all of this technical stuff down here. It takes care of everything for us. We just have to make the right assumptions. So really, I'm going to scroll down to, well, I'm going to look at this paragraph below test statistic. Oh, and also, just like in the previous section, the test statistic helps us determine what the probability is, and the probability is the p-value. If we did have to do this by hand, we would have to set up one of these three inequalities. But that's how the test statistic helps us. We treat it almost exactly the same as a z-score. And just like we did many, many chapters ago, it seems like at this point, those values help us find probabilities. We'd have to go look in the table, see, all right, is this to the left? We get the area. Do we have to subtract it from 1? Of course, we don't have to do that anymore, but one thing that I want everyone to notice, so I'm going to scroll up right fast. So when we were in the previous section, we talked about all of these steps for testing a hypothesis, and that was for the population proportion. We talked about this in the previous section. All of this stays the same for the new section, so I didn't bother rewriting it, except for one detail. There is these 3 requirements that you had to check off. Now, the top one is still true. The third one is still true. But this one changes because we don't have a P0 anymore. We don't have a P0. That's the assumed proportion value because we're dealing with mean. We don't have proportion. So that makes sense. We can't use, this formula wouldn't make sense because we're not dealing with proportion. So there's no P's. So that's the second requirement. So in your notes, I called it the second requirement. And so that's what it's referring to. And it's swapping out that second requirement with a new requirement. Let's go see what that says. So it says, we replace the second requirement, which is what I circled in the previous section, with the following requirement. Make sure you have no outliers. And you either need to be normally distributed or have a sample size of 30, at least. So no outliers, that's just one independent detail. And so really, we're not going to see any outliers unless we have a given data set. So example 1, we don't have a given data set. They just tell us everything. So we can assume that there'd be no outliers. But more importantly, we either need a normal distribution, or if we don't know that the population is normally distributed, then we need to get at least 30 samples. So that's something we're going to add here. That's the exchange with the second requirement. But besides for that, that whole table in the previous section that I just referenced, everything else stays the same. Just you're switching out the second requirement with pretty much what I highlighted. So let's go ahead and look at an example of this, because you're going to see the majority of this follows pretty much the same way as the previous section. Okay, so example 1, they tell us that the mean height of American males is 69.5 inches. And then I went and figured out the heights of 45 US presidents. You're thinking, aren't there 46? There's one president who served non-consecutive terms, so they counted him twice. There's 45 individual men who have served as president. And so their mean height, so their heights are posted on one of these POTUS websites. The mean height is 70.93 inches. Standard deviation is 2.77 inches. And we're going to treat all 45 presidents as a simple random sample. And we're going to test if US presidents are, if it's safe to assume that US presidents are taller than the average American male. Now you might just look at this and say, well, yeah, it says 70.93 versus 69.5, of course. But that's not really a hypothesis test. That's this is really a more so of a fact of intuition. And so what we're really asking for is, if we extend this idea into the future, would this hypothesis remain true? Considering we assume that there's a random sample. This is a simple random sample. Let's go ahead and see if hypothesis testing will verify this for us. If there's enough deviation between the two means for us to make an appropriate conclusion. Now, when we state the null alternative hypotheses, that's still H0 versus H1. So I'll put those off to the sides. H0 is the null hypothesis. And with the null hypothesis, well, if anything, we are not dealing with population proportion anymore. We're dealing with the mean. The mean that we're dealing with means that we use the mu notation, which is, it looks like a U, because we're dealing with means now. Now remember, the null hypothesis is always the mean value that we assume. It's the assumed value of the mean that you're trying to test. What we're saying is, we're assuming that the mean height is 69.5. This is not saying that the mean is 70.93, because 70.93 is a sample mean. We'll deal with that later. It's not a population mean, it's a sample mean. Here we're dealing with population for now. So that's the difference. And then the alternative hypothesis says, well, how are we comparing another mean to this 69.5 here? Normally, this is when we induce an inequality, and it's the same idea here. So as I read on, so US presidents are taller than the average American male. So we're trying to see if we are taller than or larger than the average American male, where the average American male, again, is 69.5.
How would you say it if you were going to make the alternative hypothesis not equal to 69.5?
Do US presidents have a height different than the average American male? Normally, they will use the word different. And then, of course, shorter for the converse inequality. So it goes on to say, verify that the requirements to actually perform this test are satisfied. The requirements, you need a simple random sample. So we talked about this before, which normally two of these we generally assume samples are independent. Which I might argue, in the most nitpicky of situations, the samples may not be independent. I don't know. There's something, George H.W. Bush and George W. Bush, since they're, related, perhaps there is some influence. Perhaps it's completely minute. That's just a thought that just popped in my head, but
What would actually make them dependent though?
Dependent in its truest form would be if one value directly affected the other. The most immediate example is if you're pulling playing cards. If you pull one card and you figure out the probability of pulling that, and then you pull another one without putting that first card you just pulled back in and shuffling. So from here, normally we assume those two for free though. I'll just say, just assume that those two are true. Those are normally always true. The one that we really need to notice is that new requirement that I threw, and that's actually highlighted at the top of the screen here. We're going to assume the sample has no outliers because they didn't give us a data set. There's no real way to check that. So, and then the population either has to come from a normal distribution and or the sample size has to be at least 30. Well, if anything, we have 45 presidents. So we don't even have to check normal distribution. It turns out it would be normally distributed because heights, anything biological in that sense tends to be naturally normally distributed. So here, sample size is greater than or equal to 30 at the minimum. So we don't even have to check. It does also end up being normally distributed, but here this is a little bit more concrete. Interestingly enough, as I did this, I realized that Abraham Lincoln was 6'4". I had no clue. Not think he was that tall. James Madison, I believe, is the shortest at 5'4". Very short man. Okay. So then it goes on to say, determine the test statistic and the p-value. Now, this is when we need the aid of the calculator. And I have the calculator tutorial in the next page of the notes, if you forget. It's fairly similar, except instead of, so the part that should be familiar is how to get to the test screen. In fact, let me exit out and refresh this. Start off with a new screen. What you will probably all see. Okay. So what you're going to do, just like we did in the previous section, you click on Stat, and you go over to Tests. We did this in the last section. What we did in the last section was we went down to 5 for the one proportion z-test, but we're not dealing with proportion anymore. And we're not even dealing with z-test because our test statistic has a t in it. All of this is a fancy way of saying we're going to use the second option. It's called a t-test. And this is related to that student t-distribution thing that you saw earlier. And you press enter on t-test, and you should see t-test at the very top. And you should see exactly all of this. Now, we are going to go over to stats because we don't have any data. So I clicked enter on stats, and as soon as you click enter on stats, you should see these, well, 4 values, and then where to place your alternative hypothesis at. So we have to find all of these values here. And I'll go ahead and write all of those and answer in part C here. So mu0 is the assumed mean in the null hypothesis. This is very similar to what we had before. We had p0, that was the assumed proportion. Mu0 is the assumed mean, which was 69.5. So if anything, we can go ahead and put in 69.5. Again, similar to before, but instead of p0, it's mu0 because we're dealing with means now, not proportions. X bar, well, that symbolism means the sample mean. Well, the sample mean, anytime you take a sample, this is of some smaller group from a larger population. The smaller group is referring to the 45 US presidents. The sample mean from them was 70.93. 70.93. Standard deviation is 2.77. And of course, n, that's the sample size. That's 45. There's 45 presidents. So those are our givens. And finally, we just need to pick the inequality symbol that matches our alternative hypothesis. Again, we did this in the last section. I'm going to pick the greater than sign because our alternative hypothesis has a greater than sign. That's it. Once you have all of these values in, and if let's just make sure it matches what we have in my my tutorial down here. It seems good. Go all the way down to calculate and press enter. And what it does is it gives you a test statistic. It's the t-value. So t0 is 463. Why not? So it gives you a test statistic, which they call t. And that t-value, if we had to do this by hand, would help you find the p-value. Now it says p is 6.007 e negative 4. And I know we've seen this before. I'll just write this kind of off to the side for right now. 6.007 e negative 4. It means you would move the decimal place 1, 2, 3, 4, accruing 3 zeros in front. So really what this is saying is that we have a very small p-value, which depending on how you're doing this study is not good. Well, if we're in the spirit of rounding to 1 decimal place, then the p-value would thus be 0.001. We are, in fact, rounding to the nearest 100,000ths place, like we did in above. E to the negative 4 means you accrue 3 zeros in front. It's always 1 less. Okay. So from here, everything follows exactly the same from the previous section. Now that we have the test statistic and the p-value, we can test at, they give us a level of significance, which is 0.05, or remember, alpha, or the level of significance, is the likelihood of committing, or the probability of committing a type 1 error. So, since 0.001, which was the p-value, since that is, and we're comparing that to this value alpha here, looks like it's smaller than alpha. Since the p-value is smaller than alpha, I guess I should ask you all at least one question. Does anyone remember what this entails? The p.
You would reject the, or not reject, but you would reject it, right?
What's it?
The hypothesis.
Which
the
one?
null hypothesis.
The null hypothesis. That's right. We reject the null hypothesis. You do this anytime your p-value is smaller than your alpha. That's why I wrote p-value less than alpha. I want to make sure I follow the book's lingo here after, because in section 10.1, we talked about the language of hypothesis testing. So if you reject the null hypothesis, then I'm going to follow what the book has. There is sufficient evidence to conclude well, ultimately you're concluding because you rejected the null hypothesis, it means there's only one option left, the alternative. So what does the alternative say? Well, it says the mean is greater than 69.5. The sample mean that we had was pertaining to US presidents. So we have sufficient evidence to conclude that US presidents are taller than average American males. I guess the average American male, singular. That's what hypothesis testing gives us. It gives us some idea of intuition and proves it using defined techniques. So again, a lot of this should be very familiar. Does anyone have any questions? And there's the tutorial that I just, for the calculator process I just talked about. So if you forget this process, you can view here. So of course on the test, as I'll probably mention Wednesday, it'll be your responsibility to probably just remember all the calculator commands. That's probably kind of a pain, but that'll be your responsibility ultimately. So let's go down to example 2. So here's one where we have a data set. Now, there's a particular type of a Snickers bar. Controversial opinion, Snickers are not very good, but that's besides the point. So they're supposed to weigh 20 grams, and there are some regulations for various places that if you do not produce product as advertised, you get penalized for it. So they want to make sure, well, definitely want to produce these candy bars over 20 grams. So they make their machine, well, they make their machine ultimately produce, on average, a weight of 20.1 grams, just to be safe. And then somebody working at the manufacturing plant is concerned about this calibration. Is it actually making Snickers of that size? Or are they smaller, which means we're going to get fined? Or does it weigh more, which means, all right, now we're just wasting product at this point. So he figures out, he just randomly selects 11 candy bars, weighs them, and then we have a table of values. So instead of them giving us all the values, like the US presidents, we have a data set here. And then we're going to use hypothesis testing to determine, should this machine be shut down? Is it not calibrated correctly? And because this is a business, they really want this level of significance to be very small, or in other words, the chances of a type 1 error occurring would be less than 1%. That's the goal here. And so when you look at this data set, you might notice, all right, some of these are less than 20, which means theoretically they could be fined if someone figured those out. But I suppose the other ones are not. So does that cause concern? Is that enough to shut down this machine and recalibrate it, which might be expensive. It might be counterproductive. So part A was kind of interesting. It looks very technical because part A is actually a problem. I'm trying to think about how to word this. Part A is actually a problem from section 7.3, where we did those normal probability plots, but they did all the work for you. So it's not really like that, but the work that they did comes from that section. So what they did a bunch of work and they found a correlation coefficient value of 0.97. I think I might have covered up 0.97 there. And the 0.97 comes from the fact that they put all of these data values, again, since it's in 7.3, you don't have to worry about this being on the test, but they took all these data values, they plugged it into the calculator in a list, and then they did the y equals stuff. You might remember this, might jog your memory, where you had to do plot on and go all the way down. So they did all of that. They took the values on the plot, they put that in L1, L2, and they found the correlation coefficient. So again, you don't have to worry about that process. We already took a test on that. But they found the correlation coefficient to be 0.97. And you might think, where's this even coming from? Why are we even doing this? The reason why we're doing this is because we're trying to verify that we can use hypothesis testing. What are the 3 conditions for hypothesis testing? I wrote them up here. Simple random sample. Samples are independent. Those are the ones we normally assume. Sample size is greater than or equal to 30. There's only 11 here. So what does that mean? We're just done with the problem? We can't use, no, that's not true. If the sample size is not greater than or equal to 30, then we need to verify that the population from which the sample is drawn is normally distributed. So we need to see, are these normally distributed? And that's what evokes section 7.3. Section 7.3 was testing if a very small data set was normally distributed. Because when you have a very large data set, you can graph it using, you can use a histogram or something like that. But if it's very small, you have to use section 7.3. So I'm only explaining where this motivation comes from. And they did the majority of the work, but it's up to us to remember what was at the very end of section 7.3. Once we figured out, so why the correlation coefficient? Why is that so important? So from a table in the back of the notes that we have used before, I think it's table 6 here. Make sure that is the correct table, right? Yes. So it's not this one actually. It's not the correlation one. It's not table 2. It's table 6 here on page 101 of the notes. If you just printed out everything recently, but what it's saying is for our sample size, and we only had a sample size of 11. There's only 11 items here. So 11 corresponds to 0.923. If our correlation coefficient is larger than 0.923, we have a normal distribution. It gives us a threshold. If it's above 0.923, then great. If it's below 0.923, don't have normal distribution. Ours was 0.97. Seems pretty good to me. 0.97 is greater than 0.923. 0.97 is greater than 0.923. So basically, our value is greater than, when I write CV, I mean critical value. We have a normal distribution, which means we do not require that we have over 30 samples, because from the limited sample size we have a normal distribution already. And so the requirement is met. or the condition is met. And I wrote on the notes, this is like example 2 from section 7.3, just to tell you all, just to motivate where this process is coming from. We have too small of a data set, which means we can't just say, all right, we have more than 30 samples, so awesome, which means that you have to check and see if your small data set is normally distributed, and that is exactly what section 7.3 did. That was all 7.3 did, in essence. Check if a small data set was normally distributed. And we pretty much skipped. We only did the last fourth of that. So besides for that, so when you get a similar problem like this, notice that all of that junk will simplify very nicely. And then we can continue as needed. Let's determine the hypotheses of the study, which again means there's an H0, there's an H1. We're dealing with the mean, so I'm putting down the mean. The assumed mean here, the machine's mean weight is told to us to be 20.1, as it says up here. It even says the word mean. So that we're just assuming that this mean weight is 20.1, and that's what we're testing. Are we actually getting about a mean weight of 20.1, or is it something different? So, yes, what's the alternative hypothesis here? What inequality symbol do we use?
Not equal.
The not equal. That's right, not equal. Because if it's less than this, you get fined. If it's more, then, well, you're wasting product. Okay. So there's the hypotheses, and then they immediately want the test statistic and the p-value. Now, for the test statistic and the p-value, I'll be scrolling back up to the data set here momentarily, because to figure out the test statistic and the p-value, you would have to go to stat and test and t-test, and well, all we know is 20.1. What's the sample mean? What's the standard deviation? I know that there's 11 of these. There's 11 data points here. What's the mean? What's the standard deviation? Wait a minute, we can just figure it out right fast. We know how to find the mean and the standard deviation of a data set. So what I'm going to do here, like I did in the previous problem, go ahead and write out, actually I'll go ahead and call it the givens. So what is given to us? U0 is the assumed mean, which we already found to be 20.1. We need to figure out the sample mean, the standard deviation. And the last one was n, which we knew was 11. Because there's 3, 6, 9, 10, 11. There's 11 values here. So we need to figure out the mean and the standard deviation of this list. Stat, edit, and we have to just type in these values. And hopefully you all remember how to find the mean and standard deviation of a list. If you quit out, it's the one variable statistic stuff just by itself. As we did pretty much in the very beginning, towards the beginning to middle part of this class. So that's, I'll call that 20.3. The standard deviation of I'll call it 0.64. It'll be 2 decimal places. So once you have all of that put in, now we can go to test and fill in our final 2. In fact, Look what it so graciously did for us. I didn't even know it did that. So it already put in everything. So if you typed, for any of you who typed it in your calculator, did it also pop it up for you? Okay, then looks like it'll do this for you. If not, just go ahead and plug them in. A little bit of approximation shouldn't hurt. And let's just make sure we select a not equal sign for our hypothesis test, because that matches our alternative hypothesis. So make sure you have not equal to selected. You calculate from there. So if you typed in everything correctly, the test statistic, which is T0, 1.04, since we're doing 2 decimal places here. And we have a larger p-value, which is good in terms of at least, well, verifying that a null hypothesis is true. About 0.32. So from here, just like we did in the previous section, this is a matter of testing the p-value and the level of significance. 0.32, 0.01, those are the two things we're comparing, the p-value and the level of significance. Looks like the p-value is larger. So this tells us we do not reject the null hypothesis. Whenever the p-value is larger. Again, let me match their wording.
So you would say that there is sufficient evidence to change the calibration.
Well, let's think about what this is saying. Since we're not rejecting the null hypothesis the null hypothesis says that everything's working fine. But the wording here, we're not, so the difference between what we had before, since we rejected one, we were left with another. Here, we didn't reject the null, but we didn't reject the alternative either. So the wording, and that's why I want to be careful about this wording. This is the wording from section 10.1. Okay, let me make sure I write this down correctly. There is not sufficient evidence where did it go? Oh, there it is. There's not sufficient evidence to conclude that, well, the mean is different than 20.1. It doesn't mean necessarily that we're accepting the null hypothesis, but we haven't really found a data set to have us, well, reject it otherwise. But this does, we're not concluding that the null hypothesis is true, but this gives us evidence that the null hypothesis is true. For the previous example, since we rejected one outright, that only left one other option available. Again, if somebody's, you know, in the United States, you're innocent until proven guilty. So if you're found, so really, you're not found innocent or guilty. They never use that wording. They say guilty or not guilty. And if you're found not guilty, doesn't mean inherently you're innocent. It just means they didn't have enough evidence to show that you were guilty.
Unless it's the federal government.
Well, I mean, we'll save that. You could save that discussion for your poli-sci class. So that's the conclusion we can ultimately make from hypothesis testing. Does anyone have any questions before we look at the last example for this whole class? What did everyone think of the NFL draft how the Saints did? Anyone watch it? No? Oh yeah, I think this is the class no one watches football. Forgot. Very rare. Okay, so all right, last example for the whole class. It is suggested that students spend 6 hours each week studying for a 3-credit-hour class. So I went and found for some given week with whatever given assignments that the top 11 students in a Math 241 class spent on whatever homework assignments there were that week. And here were some of the numbers I got. And so what I'm going to do is determine, well, do the amount of times here reflect the 6 hours per 3-credit-hour class? The first question is, what are the hypotheses? Something to do with the mean, of course. The mean equals something in the null. Actually, this is a good question. What is the, does anyone happen to see what the null hypothesis is? This one might be a little tricky. Anyone? What's that?
6 hours.
It would be 6 hours. It's in minutes.
Oh.
Kind of sneaky, but I figure you gotta make the last problem at least a little interesting. So 6 hours, you multiply that by 60, that's 360. So really the 6 hours, same thing as 360 minutes. And so pretty much we're testing to see if it is 360 or not 360. Doesn't really say anything in the context to garner anything differently. Okay, so from there, determine just the p-value it asks. So let's go ahead and figure out our givens, which means calculator is going to be a nice aid here. If anything, mu0 is 360. It's the assumed mean. Go ahead and figure out the sample mean and the standard deviation here shortly. And sample size, 1, 2, 3, 4, 5, 6. Oh, it says it right there, 11. So we can go ahead and real quickly figure out the mean and the standard deviation. Go ahead and figure out the one variable statistics for that new list.
I think you got one of your numbers wrong.
Oh, I did? Okay. 378, 200, 164, 242, 444, 73, 21, 361, 310. Aha, thank you. I did it again. Yes. There we go. Thank you for that. 452, perfect. Those should be the numbers. All right. 315 point, do 2 decimal places, I guess. Standard deviation. I'm guessing it's going to ultimately convert all of these. All it wants is the p-value. So we don't even have to give the test statistic, which we don't really need it. Calculator does everything for us. So let's go to test, t-test, and perfect. Just make sure we have 360 in here because it does not put the null hypothesis value in for us. So make sure 360 is the first value. It puts the 315, it puts in the 94, and I'd imagine it puts an N for you as well. And we want to make sure not equal to is selected, which you did this for the last problem. It should be the same. And from there, we get a p-value of call it 0.15. Let's do 0.15. Okay. And then finally, well, the second to last problem, they give us a 0.05 level of significance. Well, the p-value is 0.15, alpha is 0.05, and obviously the p-value is greater. P-value is greater than alpha. So we do not reject. We don't reject the null hypothesis. Or in other words, there is not sufficient evidence to show let's see, how can I word this? There's not sufficient evidence to show that students study more or less than 360 minutes. Can't really think of how else to word that. More or less than that. So far from this data set, it's about 360 minutes on average. And with the standard deviation as it is, it doesn't deviate enough for us to assume otherwise. So for the very last part, for the last example in this class, I will ask you all, why might the conclusion drawn, why might that be flawed? Why might this whole study be flawed?
It's less than 45, or 30. It's less than 30.
Well, we're going to assume that we did all the same stuff in the last example. That's a fair point. We're going to assume that this is normally distributed by using those methods that we talked about in the last section. So that's a good point. But we're going to assume that this is normally distributed. So let's just say this passed all the requirements. So why might this study as a whole be flawed? It's from the top 11 students. So there was a homework question that does throw that in there, and I wanted to do something similar. So it's not a simple random sample. So again, there was one problem that kind of threw this in there, and I wanted to do something similar. It's not a simple random sample, though. We're choosing the top 11. If it were truly simple random, I would just choose 11 from every student. Now, from the not top 11, you might expect a dip in the amount of minutes spent on an assignment, which may completely change our conclusion, but that would be for a different test at a different time in a different class, because that is all I have for this class. And I mean, yeah, that's it. That's all I have. I finally have my notes typed too. I'm so excited. So that's all I have for today, really. So get out a little bit early. Wednesday, I will talk more about the test. I'll have a practice test posted. We'll go through that. And that's pretty much it. Again, the test is going to be Thursday, I believe, at 8 a.m. I'll specify this again on Wednesday. But other than that, sign the roll sheet if you didn't sign it already. Have a good day.